In this lecture, we're going to talk about some of the factors that affect acid strength. pKa is affected by a variety of factors. As you can see in this example here, we have acetic acid, which is a carbon with 3 hydrogens attached. And it has a significantly different pKa from trichloroacetic acid, which has 3 chlorines attached. Also, we can see a significant difference in pKa when we compare ethanol to phenol. So there's a lot of different things that are going on here, and we're going to go over all of these factors and try to see if we can use the factors to predict pKa's. You shouldn't have to memorize numbers for the most part. There are a few that it's helpful to know, but most of the time we're just going to be comparing one thing to another to determine which one's more acidic. If we look at this chart to determine relative acidity, we see a couple things. So if you can see ethanol over here, when it has the hydrogen attached, it's considered to be an acid. And when it has a negative charge, it's considered to be a base. And notice that when we have stronger acids, like HCl, that's associated with a weaker conjugate base, like Cl-, whereas ethanol, which is a weaker acid, is associated with ethoxide, a stronger base. So you can always see these trends. The take-home message here, and the most important thing, is to know that if you have a strong acid, it's associated with a weak conjugate base, and a weak acid is associated with a stronger conjugate base. Now, we looked at this slide before, and what you want to get out of this is that charge is going to affect acid strength. Remember that if we have a positive charge in an oxygen, it is going to be more acidic than the corresponding molecule that does not have the positive charge. Let me draw an example here. So if we compare these two molecules, the positively charged species is a stronger acid than the one that doesn't have a positive charge. Also look at the amine here. Notice that the amine is positively charged, and this is a stronger acid than an amine that is not positively charged. This is considered to be acidic, whereas if you draw out an amine here, this would be considered to be a base, and it has a very, very high pKa. Let's also look at how electronegativity affects acid strength. If we're looking at the acidity of the hydrogens in blue here, you see a little bit of a trend. So the hydrogen attached to the carbon is not as acidic as the hydrogen attached to the nitrogen, and that's not as acidic as a hydrogen attached to an oxygen. In fact, the strongest acid, if we're looking at these here, is going to be HF. And if you're thinking about how this relates to the periodic table, remember that when you're looking at the periodic table, we have carbon, then we move to the right and we get nitrogen, then oxygen, then fluorine. If we flip this around, that's going to mean that our strongest base then is a negative charge on a carbon. Remember, our strongest acid is associated with the weakest base. And if we think about why this works, F-, an electronegative atom, is much better able to handle that negative charge than an oxygen. An oxygen is not as electronegative, and it doesn't like the negative charge as much. And carbon, which is the least electronegative, is going to like having this negative charge the least. So it's going to be the strongest base because it's the most reactive or the most unhappy, the least stable. The most stable is the electronegative atom. It can best handle that negative charge. We can now use a reaction coordinate diagram to compare the acidity of some of these species. So if we look at CH4, methane, compared to NH3, ammonia, we're going to assume that they have similar stabilities here. Their energy is about the same. Well, what happens when they get deprotonated? So if we take a hydrogen off of ammonia, you end up with NH2 minus. And if you take a hydrogen off of CH4 methane, we end up with H3C minus. And this molecule over here is higher in energy than NH2 minus. That means that it's harder to take a hydrogen off of methane, and that means that methane is less acidic. You can see over here that NH2 minus is more stable, or ammonia is a stronger acid than CH4. That doesn't mean it's a strong acid, of course. We just are seeing that it's slightly more acidic than CH4. Now let's talk about how size affects acid strength. If we look at HF, HCl, HBr, and HI, our strongest acid is HI. Why is this the case? Think about the size of the attached atoms. If we look at the periodic table, remember that iodine is the biggest. Let's look at this trend when we talk about stability of the base. Iodine is much bigger, so an iodine can handle a negative charge much better than a fluorine can. So in this case, this is the least stable, or the strongest base. I minus is bigger than F minus and can better handle that negative charge. Let's look at a picture, try to understand what's going on. So here's fluorine over here on the left, or fluoride, because it has the negative charge. And that negative charge is spread out over a fairly small area. When we look at Cl minus, we can see that there's a larger area where that negative charge can be spread out. So chlorine can better handle that negative charge. You're probably thinking, well, didn't she just tell us that electronegativity is going to increase acidity, and now we're looking at this size thing? How do they fit in? And so what you end up seeing is the trend for acidity is right and down, because we know that as electronegativity increases to the right, we are increasing in acidity, and also size increases acidity. So the overall periodic trend is to the right and down. And this is when we were talking about the acidity of any of these blue hydrogens. Now let's talk about how hybridization affects acid strength. Here we have an sp3 hybridized carbon. This one is sp2 hybridized, and this is sp hybridized. And what we see here is that the hydrogen that's attached to the sp hybridized carbon is the most acidic, or it's going to come off the easiest. Whereas the hydrogen attached to the sp3 hybridized carbon is the least acidic, or the hardest to pull off. This is a really large pKa, greater than 60, whereas the hydrogen attached to the alkyne at a pKa of 25 can be readily deprotonated. So why is this the case? Remember that when we talk about our carbon-hydrogen bond, this bond here contains 50% S character and 50% P character. That means that once we deprotonate it, we have a lot more S character, and the S character contributes to stabilizing the conjugate base. So our negative charge is more stable when it's in an orbital that has more S character. If we look at the sp3 hybridized situation, now that negative charge is in an orbital that only has 25% S character, and that's going to be much less stable, and this is going to be a stronger base. If you put this all together, you're going to see the following trend. Our strongest base is going to be a negative charge on an sp3 hybridized carbon, then a negative charge on an sp2 hybridized carbon, then our negative charge on a nitrogen, and then a negative charge on an sp hybridized carbon. And then we have our negative charge on an oxygen. So that's how this all fits in. And so you can see the trend for relative acid strength here. That means that an alkyne, or a triple bond, an sp hybridized carbon here, is actually going to be more acidic than an sp3 hybridized NH bond. So this is the tricky thing that you need to remember here, is that once you have an sp3 hybridized carbon, it's going to affect the acidity so much that it's going to trump that electronegativity trend where we move to the right and down. Okay, now let's talk about induction. You'll notice an interesting trend here. As we add electronegative atoms to this molecule, we are increasing the acidity. What's important to recognize here is the acidic hydrogen is the one circled in red. So in all of these cases, that hydrogen is attached to an oxygen. When we add an electronegative atom nearby, that is going to pull away electron density and by induction stabilize the conjugate base. You'll notice the effect is more pronounced when you have a fluorine, a more electronegative atom. Now this seems to be a little contradictory when we talked about our size versus electronegativity trend, but keep in mind that the negative charge isn't on the fluorine in this situation. The fluorine is just pulling away electron density. So it's kind of helping to pull away that density, and this is going to be more significant when you have a more electronegative atom. Let's draw out the conjugate base, and that might help to understand what's going on. So in this case, you have an electronegative fluorine atom, and it really wants to kind of pull away that negative charge and help stabilize it. And this effect is more pronounced when you have a more electronegative atom. Another trend that you see is the distance of the inductive effect plays a role. So if I have a bromine that's really close to the carboxylic acid, it's going to affect the acidity more. The further I move the bromine away, the less of effect it's going to have on acidity. At some point, the bromine is going to be so far away that you essentially have the same level of acidity as if it wasn't there at all. This is another picture trying to show why an electronegative group can stabilize your negative charge. So as we look at these electrostatic potential maps, here's ethoxide, and you can see our negative charge over here in red on the oxygen. And now we see what happens when we add a chlorine. So this is the chlorine, and the chlorine is pulling away some of that negative charge. You can see that the red area has decreased significantly because it's stabilizing that base. So this is a more stable anion, or a more stable base, and that makes it a weaker base. That means ethoxide is the stronger base. Again, the trend that we're looking at is seeing that electronegative atom is pulling away electron density and helping to stabilize that negative charge. As we're sharing some of that electron density, it's going to help to stabilize that negative charge and make the base more stable. With a positive charge, you are going to have the opposite effect. Remember that a positive charge is a lack of electrons. So if you have an electronegative atom and it's pulling electron density away from a positive charge that's already missing electron density, it's actually going to have the opposite effect, or a destabilizing effect. So an electronegative atom in the top case stabilizes a negative charge but destabilizes a positive charge. Another factor that affects acid strength is resonance. We can see here a carboxylic acid compared to an alcohol. Both of these have OH groups, So you might think that they have similar acidity, but the acidities are actually quite different. In fact, the carboxylic acid has a pK of about 5, whereas the alcohol has a pK of about 16. The difference is that in the alcohol, once it becomes deprotonated, the negative charge is localized on the oxygen, meaning that it's stuck on the oxygen. Once the carboxylic acid is deprotonated, the charge is delocalized or spread over 2 atoms. And if we can spread that negative charge over multiple atoms, it's going to stabilize it. So this is going to be our more stable or weaker base. So we've seen this slide before, back when we were talking about resonance, and you could see that our negative charge can be represented as being on the top oxygen or on the bottom right oxygen. In the electrostatic potential map, we like to show that negative charge is spread out over 2 atoms. When the charge is spread out over 2 atoms, it is delocalized, and hence it is more stable, or you have a weaker base. Let's look at some more examples. We have ethanol over here on the right, and its pKa compared to cyclohexanol is effectively the same. There's a very, very small difference here. But if we compare to phenol, you see a significant drop in pKa. Phenol is much more acidic. Why is that the case? Well, when phenol gets deprotonated, you have lots of resonance structures. When cyclohexanol or ethanol get deprotonated, you don't have any resonance. Here we see all of the resonance structures of phenol. So here's phenol, and if it gets deprotonated, you're going to get this molecule shown here. And let's follow these electrons to see what's happening. So this red lone pair comes down to form a double bond, and these blue electrons over here come down to form the blue lone pair. In the next resonance structure, we can move the blue electrons down to form a double bond. So the blue electrons got moved to form this double bond over here. And then we can imagine this next double bond, I'll color that pink, becomes this pink lone pair down here. So pink electrons become this pink lone pair. Then we move the pink lone pair to become this double bond over here. And in that process, green electrons come up to form this green lone pair. So the green electrons come up to form the green lone pair. And then the last thing we do, the last resonance structure, we move those green electrons over to form a double bond. And guess what? The red electrons that were there go up to form the red lone pair. So these are all of our possible resonance structures that we can get. That means that the negative charge is not localized on the oxygen, but it's spread out over 1, 2, 3, 4 atoms. It's spread out over the oxygen and 3 carbon atoms. And that is going to significantly stabilize the negative charge and make phenol much more acidic than other alcohols. You can see the same effect when you compare sulfuric acid to ethanoic acid. Ethanoic acid, I'll draw out here, and when it is deprotonated, you get a negative charge on the oxygen. So here we have the electrostatic potential map of this molecule here, the deprotonated form of ethanoic acid. Notice that the negative charge is stabilized or delocalized over 2 atoms. But what happens in sulfuric acid? Let's look at sulfuric acid. So here's sulfuric acid, and when it gets deprotonated, we get the negative charge on the oxygen. Well, if we look at this molecule, you can actually draw 3 resonance structures. We can push the electrons on the oxygen up to this oxygen and down to this other oxygen. For ethanoic acid, we can only draw a resonance structure where the negative charge goes up to 1 oxygen. So if the negative charge is delocalized over 3 oxygen atoms, this is going to significantly increase the acidity of the conjugate acid. So sulfuric acid is a stronger acid. That concludes this video on factors that affect acid strength.